All right, how exciting, our very first lecture of the summer semester. So the document you're looking at is what we call a pencast. You will see font in black and font in green. The font in green is associated with audio. So I'll open up with a quick question, and that question is, what is an equation? And I'll often write EQ for equation. And before we answer this question, I just want to address how my lectures are structured. So if you look at the top of the page, you'll see section 2.2. Now what I'm telling you there is that most of this material is from section 2.2 in the textbook. So if you want, you can go into the textbook and use that to supplement the lecture, and then I will take each lecture and break it into subsections. So you can see these subsections for this section are intro, rational equations, literal equations, and power equations. So this should make note-taking very easy and should keep things pretty well organized. And just a quick warning, I will not be following the book verbatim. So just a heads up, my lectures won't always necessarily line up perfectly with the textbook. So do be aware of that. That being said, I want to open up the class as I believe Socrates would, and that would be with a question. So I would like to ask, what is an equation? And I've been shocked. I've had thousands of students, and these thousands of students all have well over a decade of experience in mathematics classes, yet very few can actually tell me what an equation is, which is quite shocking. And the most important thing about an equation is a statement. And what a statement means it has truth value. It's true or false. So it is a statement declaring two values equivalent. So that's what an equation is. An equation is a statement declaring two values equivalent. So, for example, when I say, $1 equals 2 quarters, this is an equation. It's just false. But if I say $1 equals 10 dimes, this is also an equation, and it's true. So an equation has a truth value. It's true or false. So an equation is a statement declaring two values equivalent, and it could be a true statement or a false statement. Now, throughout algebra, we will be working with algebraic equations most frequently, and our goal there is to isolate the variable of interest. And the reason we want to do that, that's in order to figure out when the statement is true or false. So that is in order to determine when the equation is a true statement. So that's what a solution is. A solution is the conditions that make the corresponding statement a true statement. So when we're solving an equation, we're trying to figure out, hey, when is this statement a true statement? Under what conditions is it true? So solving equations in many ways is a noble pursuit of the truth. So let's go ahead and look at a few examples. Let's look at example number 1. So we want to go ahead and get x's on one side, constants on the other, and we want to use inverse operations. Now, what's cool about an equation is you have an infinite number of maneuvers you can make. You can do whatever your heart desires, so long as what you do to the left-hand expression, you also do to the right-hand expression. That's the equal part of the equation. Is what you do to one, you must do to the other. So, if looking at this equation number 1, if I so desire, I can add 10 million to both sides, and then that will not violate or mess up the truth value of the statement. But that doesn't get me any closer to a solution. So what I want to do is, let's say, well, let's add 3 to both sides. When I add 3 to both sides, then it cancels on the left, and on the right I get 2x plus 9. Okie doke. Well, let's go ahead and subtract 2x from both sides. So when I subtract 2x from both sides, I get negative x on the left-hand side, because x minus 2x is negative 1x. And on the right-hand side, I get 9. Therefore, x equals negative 9. And if you plug that in, you will indeed get a true statement. So if I plug it in, I will get negative 9 minus 3, which is negative 12. So I would get negative 12 on the left. If I plug it into the right, negative 9 times 2 is negative 18. Negative 18 plus 6 is negative 12. Negative 12 equals negative 12. True statement. That is indeed a solution. So what we have here, this is what we call a conditional equation. It's only true under certain conditions. Well, under what conditions is it true? Well, that will be a true statement if x equals negative 9. So let's go ahead and start with example number 2 now. So we'll go ahead and clean this up a little bit first. So if we distribute, let's go ahead and distribute there. So remember, when we multiply a quantity, we have to multiply every term of that quantity. So that would multiply to x thirds plus 1/3 minus 2 equals x minus 2 over 2. And what we want to do here is get a common denominator. So a common denominator between 3 and 2 would be 6. So I can get this to 6 if I multiply by 2 over 2. I can get this to 6 if I multiply by 2 over 2. I can get this to 6 if I multiply by 6 over 6. And I can get this to 6 if I multiply by 3 over 3. So what we're doing here is a very clever strategy that should be familiar to you, and that's getting a common denominator. So we get a common denominator by multiplying by 1. What's cool about 1 is we can multiply any number by 1 and it keeps its value. So that would get me, simplifying here, 2x over 6 plus 2 over 6 minus 12 over 6 equals 3 times the quantity x minus 2 all over 6. So as you can see, we got everything over a common denominator, and then we can go ahead and multiply both sides by 6. So if we multiply both sides by 6, well, multiplication by 6 is the opposite of division by 6. So that will cancel out everything. So we'll discuss this in detail later, but when clearing fractions, one way of clearing fractions when solving an equation is to get everything over a common denominator, cross it all out. And then it's business as usual from there. So let's go ahead and bring everything down, and let's go ahead and solve it. So let's simplify first. So on the left, I end up with 2x minus 10 equals 3x minus 6, distributing there. Let's get all of our x's on one side, numbers on the other. So I'll subtract 2x from both sides and add 6 to both sides. Remember, what we do to one side, we have to do to the other. So those cancel. Negative 10 plus 6 is negative 4. And here I have x. And there's our answer. X equals negative 4. Now let's look at number 3. Number 3 is quite interesting because if we go to get all of our x's on one side, suppose I subtract x from both sides, I'm left with 1 equals 3. And you might be going, well, crap, where'd the x's go? The x's have gone the way of the dodo bird. I've lost my variable. Well, sometimes your variables will completely cancel out. If your variables completely cancel out, that means there's no more variables. Well, if there's no more variables, the only conclusion left is that the only thing remaining in your equivalence relation are constants. Therefore, you can determine if it's true or false. So once all the variables are gone, we're left with the statement 1 equals 3, which is a false statement, which means this is never true. So in other words, no solution. Right? There is no condition that can make that a true statement. There is no number that when you add 1 to it, that is equivalent to subtracting 3 from it. Now, sometimes you might solve an equation. Let's look at number 4. So if we want to get x by itself, we can subtract 5 from both sides. We're left with x equals 0. That is a solution, right? 0 plus 5 equals 5. So just a quick warning here. No solution and a solution of 0 are two different things. So make sure you don't confuse 0 for meaning no solution. 0 is a solution. 0 is a real number. I have seen it in my checking account all too many times. So just be cautious there. You can't have a solution of 0. So a solution of 0 is not the same thing as no solution. And now let's look at number 5 where something interesting will happen. So if we go to solve this, we get 2x plus 4 equals 2x plus 4. And if you're clever, you'll notice, wait a second, those are the same. Well, suppose you're just going through the motions and you subtract from both sides and you notice your variables are going to cancel out. So if your variables completely cancel out, you're left with constants and you can determine if it's true or false. Well, 4 equals 4, that's a true statement. And therefore, what this means is this is what we call an identity. It's an equation that's always true. Or you can say the solution set is all real numbers. And a symbol for that is a double-striked R. So in other words, this equation here, you can feed any number into it. X can be any number you please, and it will always be true. So, just a quick warning here. You want to keep in mind that multiplication and division are distributive. So those are distributive operations. So what that means is if you multiply both sides, you have to multiply everything. If you divide both sides, you have to divide everything. It's not like addition and subtraction. Addition and subtraction are not distributive. So if you want to add on both sides, you only add once on each side. But if you multiply, you got to multiply everything. So let's go ahead and look at the next subsection, rational equations. Now we actually already touched on this. We had a previous example. If you go back to example, example number 2 on the last page, we did a rational equation. And the idea there is when solving an equation, we can use multiplication to clear the fractions. So the strategy is to get all terms over a common denominator. And then multiplication clears it out. So let's look at number 1 here. So if I look at 2, 4, and 6, I want to get everything over a common denominator. Now you might think, well, 12 is a common denominator, and you would be correct, and that's the one to go for. Now there's an infinite number of common denominators that will work here. But we try to go with what's called the least common denominator. So we want to try and get all our denominators, let me go ahead and rewrite this real quick, over the same denominator, and a common denominator between 2, 4, and 6 will be 12. So if I want to get 2 to 12, I can multiply top and bottom by 6. If I want to get 4 to 12, I can multiply top and bottom by 3. And if I want to get 6 to 12, I can multiply top and bottom by 2. So when I do that, I get 18 over 12 minus 3 times the quantity x plus 1 over 12 equals 10 over 12. So what we did there was get a common denominator. Now here's the fun part. Once we have a common denominator, if we multiply both sides by 12, skadoosh, multiplication by 12 will cancel all that division by 12. So we can bring everything down. And no denominators means no fractions. And life just got a lot easier. So let's go ahead and distribute. So make sure you distribute that negative. So that's minus 3x minus 3 equals 10. I'm going to go ahead and move a little bit quicker here. So if we combine like terms, we get negative 3x plus 15 equals 10. Negative 3x equals, let's see here, negative 5. Therefore, our answer is 5/3. All said and done. Now let's go ahead and look at the next example. So this next example, number 2, is similar in concept to the previous, but now we have a variable in the denominator. So don't despair, our strategy remains the same. We want to get everything over a common denominator. So let me go ahead and rewrite it. And that's our current strategy right now, is get everything over a common denominator. That's our goal right now. If we can get that common denominator, we can clear all the fractions. So if we clear the fractions, life gets easier. So if we look at it, we got 3 terms. And 2 of the 3 terms have a denominator of x minus 4. It's only the first term that's missing it, so let's patch it in. So we can multiply top and bottom by x minus 4. Now I want you guys to really understand why. Understand the why of it. I can multiply 2 by x minus 4 over x minus 4 because all I did there was multiply by a giant 1. Now if you do that, get that common denominator, multiplication by x minus 4 clears everything out. We can go ahead and bring everything down so it's a little bit cleaner. Plus 5 equals x plus 1. So if we distribute 2x minus 8 plus 5 equals x plus 1. Let's go ahead and combine like terms. 2x minus 3 equals x plus 1. So subtract x from both sides. Add 3 to both sides using inverse operations. And you're left with x equals 4. Now, we have a problem here. Go ahead and try plugging this in to check your answer. And if we go to plug this into the original statement, we're going to get 5 divided by 0. So we have a problem here. This solution causes division by 0. That means it doesn't actually work. Division by 0 is an undefined value. One cannot divide by 0. Such a quantity does not exist. So number 2 is actually no solution. So the warning here is you have to make sure your solution does not cause division by 0. Right. You have to make sure your solution does not cause division by 0. If it causes division by 0, then that means it doesn't work. We have a special name for that. That is called an extraneous solution. So an extraneous solution is a solution that does not work. So why do we use the word solution then? Well, it's a solution in the sense that you do everything right, but anybody who's lived life long enough knows, hey, sometimes you can do everything right and it still doesn't work. Well, that's also true in math. Sometimes you can do everything right in solving an equation, but the answer won't work. Why? Because complications. What's an example of a complication? Division by 0. That is like the classical complication in mathematics. So anytime you have variables in denominator, be wary of division by 0. Alright, that's a potential complication that could occur. So let's go ahead and look at another example. Let's look at example number 3. Now, what we're going to have to do first is we're going to have to factor. So this was in the Intro to Online worksheet, and factoring is probably the most important prerequisite skill. So there's nothing to factor in the first denominator, nothing to factor in the second denominator, and this third denominator factors into x plus 1, x minus 2. And again, factoring is one of those prerequisite skills you need to know coming into this class. It's probably the most important prerequisite skill. So please make sure you brush up on your factoring, otherwise you're going to have a very, very, very rough time in college algebra. So if we factor it, we can see what the common denominator is. So we can see that this denominator here has x plus 1 and x minus 2, and that's our common denominator. So our first denominator is missing a factor of x minus 2. Let's patch it in top and bottom. The second one is missing a factor of x plus 1. Let's patch that in top and bottom. Now we can see all denominators are the same, so multiplication by the common denominator will clear out all of that division, and we are left with a much simpler statement, bringing everything on down. So let's go ahead and solve that. We can go ahead and distribute. So it's 2x minus 4 plus 3x plus 3 equals x. Let's combine like terms. So 2x's plus 3x's is 5x's. Minus 4 plus 3 is minus 1. So we got negative 1 equals negative 4x. Divide accordingly, and there's our answer. And if we go back to the original statement, we know x can be any number so long as it's not negative 1 or 2. Those are what cause division by 0. So if we look at the original problem, we see, hey, if x is negative 1, we're going to get division by 0. And if x is 2, we'll get division by 0. So any answer is okay so long as it's not 2 or negative 1. And we got a quarter, which is fine. Let's go ahead and move on to the next subtopic, literal equations. So literal equation is we're just working with a multivariate equation. Now it looks scary, but it doesn't change our strategy. We still want to clear fractions first. So if we look at this equation, we want to solve this for x, which means we want to go ahead and get x by itself. So we need a common denominator between 3 and 5. Well, 15 will do the trick. And we'll multiply this guy by 3 over 3. So our denominator is 15, so we clear those out, and we're left with 5y equals 30x plus 3. So we'll go and subtract 3 from both sides. Now you can't combine those terms. That's fine. Just write it as it is. That's 5y minus 3 equals 30x. Divide both sides by 30, and there you have it. There's our answer. X equals 5y minus 3, all divided by 30. So, when you're solving a multivariate equation, you will not get a numerical solution. You will get an algebraic solution. If you actually go back and plug that in, you will arrive at a true statement. So we just want to make sure we clear the fractions first. Now let's look at number 2. Something interesting will happen here. We want to go ahead and get all of our x's on one side. So suppose I subtract 3x from both sides. You'll notice we can't combine those. Okay, fine. Let's go ahead and bring it on down. So we have xy minus 3x equals 1. So xy and 3x are not like terms. Again, if you need to, go back to your prerequisites and review what like terms are. We can only combine like terms, and those are not like terms, so we can't combine them. So the question is, well, how do we get our pos on the x? Well, our trick there is if our variable of interest is in multiple terms that don't combine, we can factor out that common factor of x. So if we factor out the x, we arrive at that, and then we can divide both sides by y minus 3. And we arrive at our solution. Alright, cool beans. So just a quick little tip there, if the variable of interest is in multiple terms that won't combine, factor it out. So let's look at one of my favorite examples. This is an excellent example for a college algebra class. And we want to get z by itself. So here the name of the game is to isolate z. So we want to get a common denominator. So this one's missing yz, this one's missing xz, so patch it in top and bottom. This one's missing xy. So multiply accordingly. And then if we multiply both sides by xyz, all of that clears out. So let's bring it on down. We have yz plus xz equals xy. And now we want to isolate our variable of interest. So we want to get z by itself. And we notice in the left-hand expression that z is in two terms that don't combine. So the trick here is to factor it out. So once we factor it out, we can then divide accordingly. So that's z times the quantity of y plus x. Well, we use division to cancel out multiplication, and we arrive at our algebraic solution. So there's that. Alright, let's go ahead and wrap up the lecture with power equations. So power equation is when you have a variable raised to a power. This is where, of course, n and m are integers, c is a constant. Now, there's two scenarios with a power equation. If it's an odd power equation, you will have a singular solution. If it's an even power equation, you will have a pair of solutions, and we'll need a plus or minus sign. So, for example, let's look at let me go down here and just make up a quick example. Suppose you want to solve x squared equals 4. Well, the opposite of squaring is power of 1/2. You type that into your calculator, you get 2. But the actual answer is plus or minus 2. Because 2 squared is 4, but negative 2 squared is 4. That's because negative times negative is positive. So anytime you have an even power equation, you'll have a pair of solutions. So the trick with a power equation is to use that reciprocal power. So the reciprocal of 5 is 1/5. So we're going to raise both sides to the 1/5. And we get 2. So 32 raised to the 1/5 is 2. Now, I want to clarify something here. I did not multiply both sides by 1/5. I raised both sides to a power of 1/5. Multiplication by 1/5 is very different from an exponent of 1/5. So at this point in time, pull out your scientific calculator and type that in. 32 raised to the 1/5. You should get 2. So feel free to go ahead and hit the pause button right now. Make sure you know how to type that into your calculator. Depending on your calculator, you may need to add some parentheses in there. Now, let's move on to the next example, number 2 here. Before we use those reciprocal powers, we need to isolate. So I'll add 7 to both sides. And then divide both sides by 2. Which is 5. And let's go ahead and solve that. So we will need a plus or minus there. So it's going to be plus or minus 5 raised to the 1/2, which is the same thing as plus or minus square root of 5. And again, if need be, if you have to go back to your prereqs, this is where you might want to review rational exponents. Again, that's material you're supposed to know coming into this class. Alright, so go ahead and wrap up with 2 more examples. So if we look at number 3, we want to isolate first, subtract 1 from both sides. And then divide both sides by 9. And then raise both sides to the reciprocal power. The reciprocal just means flip-flop. So the reciprocal of 2/3 is 3/2. Now, you got to look at the original, and you look at the original exponent, you got to ask yourself, hey, is this an even power equation or an odd power equation? You always look at the numerator of the original power. This is even, which means you need a plus or minus. You'll have a pair of solutions. So that will simplify to plus or minus, that'd be 8 over 27 when you simplify. And again, if need be, review rational exponents. And so we'll look at this last example. The reciprocal of 3/2 is 2/3, so we want to raise both sides to the 2/3, and that will get us 4. And we do not need a plus or minus here because this is odd, so no need for the plus or minus. So just a quick warning here. Don't forget that plus or minus on even power equations. You don't want to forget that plus or minus on even power equations. They have to be even. The odd ones are fine. The even ones will have a pair of solutions. So if you forget the plus or minus symbol, you're forgetting half of the solutions. Alright, well that is a wrap for the first lecture of the semester. You are now ready to complete Worksheet 1. I've covered everything that's on Worksheet 1. So keep up the hard work and let me know if you have any questions, and have a wonderful day.